Hello everyone! Today in our explainer, we're going deep on a physicist whose work is, quite literally, the invisible foundation of our entire quantum age.
That's right. And we're diving into a really fantastic essay by Jörg Owe Schnappet to uncover a story that all starts with what sounds like an impossible challenge.
So, welcome to our quantum deep dive. And let me just start by asking you to imagine a task that sounds like it's straight out of science fiction, something that just shouldn't be possible. How do you grab a single particle, something way, way smaller than an atom, and just hold it perfectly still so you can study it for weeks or maybe even months on end?
And you know what? Let's raise the stakes. What if that particle is antimatter? You know, the stuff that annihilates the very second it touches normal matter. How in the world do you build a container for something that can't touch the walls? Or, on a different note, how do you build a clock so incredibly precise it would barely lose a second over the entire age of the universe?
Well, these aren't just wild thought experiments. These modern marvels are very, very real. From quantum computers to the mind-bending antimatter work at CERN, and all of them, every single one, depends on cracking that one core problem: how to trap and control single-charged particles with a precision that is just almost impossible to imagine. So the big question is, where did this solution even come from?
And the answer? Well, it might just surprise you. Because to find the origin, we have to go way back. Not to the era of supercomputers in Silicon Valley, but all the way back to the 1930s to meet a quiet, unsung architect of our entire quantum infrastructure.
And his name was Frans Michel Penning. He was a Dutch physicist working at Philips. And get this, he wasn't trying to build a quantum computer. He was a classical physicist working in a time when the whole quantum world was still this brand new, incredibly strange frontier.
So, Penning was born back in 1894, and he really came of age, academically speaking, at the University of Leiden. And you have to understand, Leiden at that time was an absolute powerhouse of experimental physics. He was surrounded by these brilliant minds, especially the Nobel laureate Heike Kamerlingh-Onnes, the guy who discovered superconductivity. And that environment, well, it shaped him profoundly. He was just steeped in the motto of his mentor, Kamerlingh-Onnes, which was door meten tot weten, or through measurement to knowledge. And this really became Penning's North Star. It's this core belief that real understanding doesn't just come from elegant theories on a blackboard, but from the hard, nitty-gritty work of precise, careful measurement.
Okay, so armed with this philosophy, Penning goes to work at the Philips Research Labs. And his first huge discovery actually came from studying something that was pretty common technology for the era: gas discharge lamps. You can think of them as the great ancestors of our modern neon signs and fluorescent lights.
Yeah, and while he was studying these gas mixtures, Penning stumbled onto something completely new. He figured out that a highly excited, but still neutral atom of one gas could basically pass its energy over to an atom of another gas, and in doing so, knock an electron off and create an ion. This process, which we now call Penning ionization, was just a much smarter, more efficient way to create ions than simply blasting them with electrons. And here's the key. He found a really clever, indirect way to generate the charged particles he wanted to study.
Exactly. So making the ions was step one, but they're incredibly flighty. They're just zipping all over the place. How do you possibly trap them? I mean, how do you build a cage that literally has no walls? This was the next great challenge, and solving it, well, that would become his most famous and lasting invention.
The absolute genius of the Penning trap is how it elegantly combines two different fields. First, you have this powerful magnetic field that grabs a charged particle and forces it into a super tight circular loop. So boom, it's trapped side to side. But it can still slide up and down that magnetic line, right? So Penning added this specially shaped electric field that creates what you can think of as an electric valley. If the particle tries to drift up or down, this field just gently nudges it right back to the center. It's like a magnetic vortex sitting inside an electric valley, the perfect little prison for one single particle.
Now, it's worth pointing out that there is another famous ion trap out there, the Paul trap. But the key difference is that the Penning trap uses static fields that don't change. This makes it unbelievably stable. It's like a calm, deep valley where a particle can just rest for months. The Paul trap, on the other hand, uses oscillating fields. It's more like constantly juggling the particle to keep it in place. For ultimate, long-term stability and precision, Penning's static design is still the undisputed champion.
And with this new tool, this champion of stability, scientists could finally do what everyone thought was impossible. They could literally isolate one single particle from the rest of the universe and study its properties with the level of accuracy that, honestly, it's hard to even wrap your head around. Just take a look at this number. This is the g-factor of the electron, which is basically a measure of its magnetic moment. This is one of the most precisely measured quantities in all of science, and how did they measure it? You guessed it, by trapping a single electron in a Penning trap for months on end and just probing its properties. This measurement is one of the most incredible, stunning confirmations of our best theory of matter and light, which is quantum electrodynamics, or QED.
To try and put that insane precision into perspective, it's the equivalent of measuring the distance from New York City all the way to Los Angeles and getting it right down to the width of a single human hair. That is the kind of power Penning's invention unlocked for science. It's just amazing.
And because of that incredible power, Penning's legacy is so alive and well today. I mean, when you look at the world's leading physics labs, CERN in Switzerland, NIST in the US, the Max Planck Institutes over in Germany, their most cutting-edge, groundbreaking experiments, from trapping antimatter to building the best atomic clocks, they all stand on the foundation that Frans Penning built nearly 100 years ago.
Okay, so let's bring this full circle. At the very beginning, we mentioned all these incredible modern technologies. Now we can finally connect the dots and see exactly how Penning's work from way back in the 1930s is the essential, unseen foundation that they are all built on top of.
It's everywhere. In quantum computing, ions held perfectly still in Penning traps are some of the most stable qubits we've ever created. For atomic clocks, a trapped ion gives you a tick that is just unbelievably stable. At CERN, look, these traps are the only technology we have to hold on to antimatter long enough to study it. And in advanced mass spectrometry, they use the exact same principle to weigh molecules with breathtaking accuracy. This isn't just an influence, it is the core component.
And nothing shows his foundational role better than this quote. This is from Hans Demhelt, who won the Nobel Prize in 1989 for refining the ion trap technique and for making those ultra-precise measurements we were just talking about. He didn't just give Penning credit, he called Penning his scientific ancestor. That's such a powerful way to acknowledge that intellectual lineage, from one master to the next.
So what's the big takeaway from all this? I think the most crucial point is that this amazing quantum future that we're all so excited about today, with its promise of unbelievable computers and incredible new sensors, it's all deeply, fundamentally rooted in the brilliant, practical, hands-on work of classical physicists like Frans Penning.
That's exactly right. Penning's greatest legacy wasn't some abstract theory. It was a physical tool. He was an inventor, an engineer of science. He didn't just observe the world, he built a machine that allowed all of us to trap a tiny piece of it, to hold it up to the light, and to see it with a clarity that no one had ever even imagined was possible. He built the key, and that key opened the door to the entire quantum realm. And all of this leaves us with one last thought. Penning was this quiet pioneer. He was working on industrial problems in the 1930s. He had absolutely no idea his work would one day be used to trap antimatter or build quantum computers. So it really makes you wonder, doesn't it? What fundamental tools are being built in labs right now by today's unsung pioneers that we've never even heard of that will become the foundation for the wonders of the next century? Well, today's deep dive was based on the really insightful essay by Jörg O.A. Schnappert. You can find out more and read his work at schnappert.de.
Thank you so much for joining us. Goodbye for now.
Schnappert.de is a private project by Jörg O.A. Schnappert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.